Sir, can we start, sir? Pradhan, sir.
Yes, we can start. No problem.
Okay. A small introduction, sir.
Okay.
Bonishri, ma'am.
Are you there?
Bonishri, ma'am.
Yes, sir.
Yes.
It is great honor to introduce this session 3, day 2 chief guest, Dr. Pradhan sir. He has completed Master of Technology and Doctor of Philosophy degree in Nano Electronic Devices, Electrical Engineering Department from National Institute of Technology, Roorkela, Odisha, India, in 2013 and 2017 respectively. He has been awarded the prestigious Sri Patra Gold Medal for Best PhD Thesis by National Institute of Technology, Roorkela in 2018. Post PhD has worked as a senior project engineer in Nano Lab Electrical Department, Indian Institute of Technology, Kanpur. And consequently, he has worked as assistant professor in EC department, JP Institute of Information Technology, Noida, from July 2017 till March 2018. Currently, he is working as an assistant professor in EC department, Indian Institute of Information Technology, Design and Manufacturing, Kanchipuram, since 2018. He has authored or co-authored over 80 plus international journal and conference articles. He has been honored and received recognition from IEEE Madras section for publishing in IEEE transactions or journals in consecutive years 2019 and 20. He also listed in the golden list of reviewers for 2020 IEEE transactions on electronic devices. His research interests are in the area of modeling and simulation of nanoscale devices, silicon and insulator FETs, graphene FETs, and NC FET solar cells reliability of devices. Dr. Pradhan is the senior member of IEEE and IEEE Electron Devices Society and also a life member of Solar Energy Society of India and Institute of Engineers. Welcome, sir. You can occupy the forum.
Thank you, ma'am, for such a nice introduction. So, a very good afternoon to one and all present here. And I was just going through the brochure, and it's such a wonderful, systematic, organized from starting from theory to practice sessions. I think modeling MATLAB is there, and Centeros is there, S process and S device, and all theoretical aspects also, quantum computing, spintronics. So all the aspects have been touched carefully by the organizers. So I thank all the organizers, and basically thank you, Dr. Charles, Praveen, and team of EC department, Kalasalingam Academy of Research and Education for organizing this FDP on future perspective of semiconductor devices. And welcome all participants to this third session of second day. I think after Dr. Nirmal and Professor Karmalkar. So this will be the third session. And it's a challenge for me because post lunch session, and it's the last session of the day. So I'll try my best to hold the participants, not to bore anyone. Okay. So anyhow, let me share my screen and start this session. Okay, so I think my screen is visible to all of you. So it will be my honor and privilege to be a part of this FDP. And I have prepared just a generalized talk because more specific talks are already covered by Dr. Nirmal, Professor Karmalkar, and your Professor Kaushik, and everyone is taking care of all this spintronics and quantum computing, nanowares and Centeros. So everything has been covered by all, even ITRS and IRDS, as I was going through the brochure. So IRTS and IRDS also taken care by Dr. Nirmal. So let me give you a brief about the whole topic, whatever we are doing here in my institute. and in my group. So today I'll talk about nanoscale devices. So what are the challenges and opportunities? And as already Madam has introduced me, I'm Dr. Pradhan from Indian Institute of Information Technology Design and Manufacturing, Kanchipuram, so which is located in Chennai. And this is my email ID and personal website. So if you have any doubt in today's session or any queries, you are free to ask, or even you can drop a mail if you have any still doubt in later point of time. So definitely you will get a reply. So let me introduce my group. So here are some of the PhD scholars and some masters and undergraduate students, and some alumni. They have joined in higher study or in some companies, industries. So some people joined National University of Singapore in US, and some in Pennsylvania, and some people is they are working in Intel and XP Semiconductors. So all these things, and mostly my group is focusing on modeling and simulation part, because we are not doing any fabrication aspect. So basically FinFETs, silicon on insulators, graphene FETs, and negative capacitance FETs, which is nowadays booming in the research industry. And again, BioFETs, or even you can say dielectric modulated FETs, and junctionless FETs, and whatever the linearity and reliability issues in devices. Basically, this focused on ion irradiation effects, heavy ion or something else. Also, the simulation and results, and some of the hot areas like neuromorphic devices. So, where basically people are nowadays talking more on artificial intelligence and neural networks. So these devices also can be a part of this neuromorphic devices. So that also I'll little bit talk about. And I didn't focus solar cell here because it will be a separate topic, and the time is very limited. So I'll only focus about this MOS devices or FET-based devices, not on solar cell devices. So solar cells, so we are also working in trinitride and gastride based solar cells. And today I'll talk fast up. I'll cover this nanoelectronics. What are the scaling and benefits, challenges, and some feasible solutions, and what are the emerging devices to follow further MOS law, and then little bit about applications like dielectric modulated FET, then how to detect any biomolecules, anything. It may be DNA biomolecules, it may be something else for some other disease. Then some open areas, like open areas in the sense neuromorphic computing, power devices. Power devices means which other materials or devices can be useful for power electronics, or who can sustain high power or high voltage, all these things. That also I'll little bit cover. And further, this negative capacitance NCFET and nano seed transistors. So these are the nowadays emerging areas to work in the devices area. So let me start my fast talk. So first one is about scaling. So scaling, I think everybody is familiar about it. So why we need transistor become smaller and interconnects become shorter? Because we can integrate more number of transistors into a single chip, so that we can increase functionality as well as we can decrease the cost. So two parameters, one is functionality, another one is cost. So that is why definitely if you can able to reduce the size, so capacitance obviously decrease because it depends on this area and distance. And further, this delay tau, which is nothing but CV of an I. So if capacitance decreases, then we can able to reduce the delay. And delay means we are increasing the speed. Nothing else. We are increasing the speed. So which is a requirement. So basically, scaling is essentially aims towards higher speed and low power and higher packet density. So that is why I just mentioned a quote here. To improve the performance or to integrate more functions into a chip, always small is desirable. Okay, so we started with bulk, and then microelectronics came, which is nothing but VLSI or microelectronics that make sense and become very much popular. Then nowadays people are talking about nanoelectronics, and it is going to, I don't know how it is going to end, I think, because 2 days back TSMC announced its 3 nanometer technology. It is going to mass production in next year, I think, towards the end of 2022. So we don't know what will come next after nanoelectronics. So start with MOS law. So this taken from TSMC only. What is the 7 nanometer process and integrating 6.9 billion transistors. So if you see, look into this graph, which is talking about year and number of transistors. So just I have taken here up to 2015, which is nothing but 14 and in between 14 and 7 nanometers. So now again 5 nanometer is in mass production. So two things. So one is more Murray, another one is MTM, which is nothing but more than Murray. And more Murray means it started continued shrinking. They didn't focus anything else about apart from shrinking. So what is the target here? Target is speed and power, how to increase the speed, how to reduce the power, and the cost per functionality. So how to minimize the cost. That is why continued shrinking in more Murray. And if you talk about MTM, so MTM is functionality diversification, where we can integrate more number of functions into a single chip. Either it may be analog digital or analog RF, digital RF. So all the components are just integrated into a single chip that is giving us SIP or SOC kind of thing. System in package or system on chip, all these things are possible because of this MTM. And continued same thing. So if you see what is a 0.7, the 0.7 number is a holy number in this scaling era. And how it is a whole number, if you find out 0.7 into previous width and 0.7 into previous height, so it will give rise you 50% or nothing but 0.49, which is equivalent to 50% of the half of previous area. And this, by following all the maximum foundries are following this this rule, thumb rule you can say, and it started. If you see this diagram, this is more Murray, and how we can continue scaling here. And if you see this x-axis, it is nothing but functionality diversification, which is we are integrating analog, RF, passive components, active components together, high voltage power components. So all these things are merged together and giving you MTM or functional diversification. Now here we started scaling down the device from, I just taken from 2003 to 13. This is the old table from ITRS only. I think Dr. Nirmal will give you more idea about International Technology Roadmap for Semiconductors or IRDS roadmaps. So here, if you see, this we started 2003 19 nanometer technology, and here till 22 nanometer technology in 2013. So basically there are two applications. So one is either you can go for a high performance or you can go for a low standby power. So high performance, that means, for example, our systems or personal computers where we do not bother about the power consumption. So we only need the speed or performance. So that is why this is high performance computing or HP. And the second one is low standby power. If you talk about mobile phones where we are more concerned about the battery backup. So this is LSTP. And if you focus to applications, so somehow this is LG gate length, and gate length is 37 nanometer for 90 technology. For HP, not for LSTP, because LSTP we are more concerned about leakage or you can say battery backup. So that is why LG is little bit high, 65. And if you compare the on state and off state currents, so on state current is 1100 microamps for HP, and whereas for LSTP it is only 440 microamps. So we can little bit compromise with the performance or the speed in case of LSTP, but we should concern about the leakage part. So here, if you look into this I off, which is 0.15 microns here, and in case of HP, but if you see in LSTP, it is too low, that is 10 power minus 5. So in this way, you can compare for all 65 and 45. And again, one more thing here, if you multiply 90 with 0.7, that may give you near to 65. Similarly, 0.7, it may give to 45, and it will still go on. And the technology came here. What is strained silicon? So strained silicon means nothing else. It's a merge between silicon and germanium. So if you look into the lattice constant of silicon, it is something 5.43 Armstrong, and similarly for germanium, it is something 5.46 Armstrong, or it's quite different from silicon. Okay, so if you are merging these two materials, so definitely there will lattice mismatch, and in the junction we may experience some amount of stress or strain. So that will further enhance our mobility, and we can get high on current. So this strained silicon came, then high K metal gate. So how to reduce the offstate gate leakage? So that's why one good insulator we need. So instead of SiO2, because SiO2 the permittivity is very low, 3.9. So people started exploring high dielectric materials or high permittivity materials in gate insulator. And further, finally, this new structure, which is nothing but FinFET or other device structure, even nanosheet also people are or foundries are trying to mass production this structure. So scaling for cost, speed, power, and new technology every 2 years. So channel length reduction is basically 30% we are doing, and area reduction, as I have shown you, 0.49, which is nothing but 50% reduction in each new technology. And this one just from a Intel roadmap. So Intel roadmap, same thing, 90 nanometers silicon germanium or a strain technology, then further high K metal gate. So here you can see high K metal gate. These all are SEM figures. And 2011 or 12, they started FinFET, adopting FinFET, and all the other foundries also started using FinFET. And now there is this late news, I think June 2019. So there's a article came, what should be next. So there's a fighting in between 5 or 3 nanometer. So Samsung is saying, okay, we'll release 3 nanometer. TSMC is saying something else. So all these news are there if you follow semiconductor engineering. So all the articles are coming there. And one more article I was just reading 2 days back. So June 19, 2021. So here TSMC roadmap calls for 4 nanometer process this year, and 3 nanometer in 2022. You can just the participants can go, and interested participants can go and read this article. It's a very good article. And so last year, what I was just summarizing this, last year TSMC started 5 nanometer, which is iPhone 12 series. They are using this 5 nanometer process node, and again they are announcing 3 nanometer process node during second half of 2022. So 2022 second half, they're planning to release this 3 nanometer processes. And in between, because now 5 and 3 in between, there are also a plan to produce 4 nanometer chips later this year. And if you compare 3 nanometer process node, it is like 15% speed and 30% less power as compared to your 5 nanometer process. So there is a target to achieve this 15% speed and 30% less power for 3 nanometer process node. And further, this article also says TSMC and Samsung foundry, they plans 2 nanometer in future, not 2022, maybe 23 or 24, something else. And after that, what? So next will be what? There is a big question mark. And in this article, finally it is mentioned, but what happens after that is definitely up in the air. For now, we don't know, it is in air. And now again, if you see, everything will come with a payment. We cannot achieve everything without paying for it. So we have to pay certain amount. So what is the payment here? Because you see all the advantages of scaling, but there are certain challenges, certain cons. So what are the cons? So here are the challenges. So these challenges are cumulatively called as short channel effects. So what is this? Source drain to channel electrostatic coupling, and we may lose this coupling. Again, there is a transport limitation, because mobility silicon mobility is going to be restricted, and it is no more enhanced further, because we tried strained. Now people are searching about some different materials. So here I'll talk about graphene and other 2D materials a little bit, because there are a lot of materials, graphene and MOS2, molybdenum disulfide, and tungsten disulfide, WS2. So all these materials are having only 2 dimensions. They don't have 3 dimensions like silicon or germanium or other semiconductors. So the advantage of 2D semiconductors, so they are supporting ballistic transport. So instead of zigzag manner, the carriers can travel from source to drain with the speed of bullet. It's kind of bullet, so it supports ballistic transport, and all the mathematics and physics, it will change if you are incorporating the graphene or any other 2D materials. That also I'll show how to model graphene FET. And then what are the parasitic effects? So parasitic means there are a lot of capacitance and resistances, maybe source and drain capacitance and resistances also, they are coming to picture. And one more interesting part here, that is Boltzmann tyranny or Boltzmann's limit. So it's popularly called as Boltzmann tyranny. So Boltzmann tyranny says for an ideal MOSFET, we cannot go beyond 60 millivolt per decade. The subthreshold slope, if you make a logarithmic IDVG, and if you look into the slope of log IDVG, so that slope, there is a limitations, and it cannot go below 60 millivolt per decade. So if it is unable to go below 60 millivolt per decade, then the leakage current, we are it is uncontrollable, and it's very high. So our interest is how to limit this offset leakage by reducing the subthreshold slope. So that I'll focus about negative capacitance FET, how NC FETs are popular to reduce this Boltzmann tyranny. So all these issues little bit briefly I'll talk, because these are theory, and I hope all the participants are aware of all these things. But let me just briefly cover all this. So why these short channel effects are coming to picture? If you compare these 2 diagrams, so one is long channel device, another one is short channel device. Now you just think about these 2 depletion widths. So here one PN junction, if you think about, this is N channel, so N plus and P, and here also it is N plus P, and you can just imagine there is a depletion width here, and there is a depletion width here, PN junction, and this junction width is in nanometer, is in terms of few nanometers, something like that. And in case of long channel devices, the channel length is in terms of micrometer, and which is very large as compared to this junction width, and it can be neglected. So this effect of junction width can be neglected as compared to channel length. But if you come to short channel devices, the channel length is also in nanometer, and this junction width is also in nanometer. Okay, right? And you cannot ignore the effect of this junction width, because everything is in nanometer. So here we need to consider all these effects or all this impact, whatever coming to picture because of this junction width. And that is why all this Dibble effect, or you can say drain induced barrier. So where the drain bias is taking care of the junction barrier height, or here the barrier height, source side barrier height, and which is only taken care by gate. The gate should be the only controller, not the drain bias. So again, if you go beyond drain induced barrier layering, then it may punch through come. So what is a punch through? That means these 2 depletion widths merge together, and it will give rise you punch through. And what is surface scattering? There are a lot of scattering mechanisms. Maybe phonon scattering, maybe surface scattering. So due to this scattering effect, again mobility, there is a restriction or limitation. You cannot go beyond certain amount. So mobility is also restricted by scattering. Again, velocity saturation. So velocity saturation, that is a interdependent of electric field, and your electric field is quite high because all the dimensions are in nanometer. So if you divide volt per nanometer or meter, so you'll get electric field in terms of 10 power 9, something like that. So velocity saturation is also one dependent of electric field, and due to this high electric field, we are unable to achieve large mobility, or you can say V is mu E, and mu is restricted, so electric field is keep on increasing. That is why velocity is going to saturate. That also I'll show. So due to this limitation, drain current is again one factor which is limited or saturated. And the hot electron effect is coming to picture again due to high electric field. And last, this Boltzmann tyranny, whatever I spoke previously, 60 millivolt per decade. So just take one by one. So here first one is the drain induced barrier lowering. Just you can compare this diagram. So one is long device, one is short device. So this long device and short device, I just taken 3 dimensions. One is you can just see 2 micrometer channel length, another one is 0.2, and third one is 0.35. So I can just make a comparison between this 2 micrometer, which is long channel, and another one is 0.2, which is term-based short channel, and 2 drain biases. So in 2 drain biases, just focus on 2 micrometer case. So if you look into 2 micrometer case for 2 different biases, so one is 3 volt, another one is 50 millivolt. Just look into this slope, and these in case of subthreshold regime, there is not much change. The difference is almost equal, and drain induced barrier, or you can say drain bias is not hampering any device performance in the subthreshold region. But now if you compare this short channel device for 2 different biases, so one is 50, another one is 3, you look into this picture. So one solid line here going, another solid line is here, and you can see the huge difference between 2 lines with for 2 different biases. So that means drain bias is taking care of all control, and your slope, your leakage current, everything is taken care by drain bias, which is not desirable, because our gate should be only controllable. And due to this drain induced barrier lowering, so drain bias is taking care of the barrier height, and that is why VT decreases and offset leakage is high. So all these things are coming. Now second one is surface scattering. So what is surface scattering? Again, if you look into the earlier case, the horizontal channel length, it's too high, or you can say there are 2 electric fields. One is vertical, another one is lateral. So vertical electric field obviously too high because of oxide thickness. Oxide thickness is in terms of nanometer. Now you can divide gate bias with oxide thickness. So vertical electric field obviously high. Now you can look into the horizontal or lateral field. So lateral field is also becoming high because of length is shorter, and it is in terms of nanometer. And you can divide VDS divide by L. So VDS divide by L, that will give rise you your lateral electric field. So both the electric fields are coming to picture. We cannot ignore the lateral field also. So if both the fields are coming to picture, then resultant may come as zigzag manner. So resultant zigzag manner means your carriers will travel like this. Again, it will collide with this junction. Again, it will come and it may collide with another atom or this surface. So it will go like this, which is taking much time from one source to drain point. So that is why we are limited by this scattering mechanism, and the current is minimizes, or you can say the mobility is also degraded. All these things happening due to surface scattering. And third one is velocity saturation. Just I'm quickly finishing all the what are the short channel effects. So this again, like I told, the relation drip velocity is nothing but mu into electric field, and here is the key factor, mobility, and which is restricted due to scattering. Again, if your electric field is keep on increasing, you cannot increase further velocity. Velocity is restricted due to this high electric field and mobility compensation. So because of this, again, drip velocity is saturated here. Instead of keep on increasing, it is saturating somewhere, and our current is limited to that point. So here, velocity saturation. And finally, that is Boltzmann limit. So what is the Boltzmann limit? Just look into this diagram. One is log ID, another one is BGS. This one is linear scale, this one is log scale. And in this log scale, our focus is here, subthreshold slope. And this subthreshold slope should be as low as possible, so that this line will go and collide somewhere here, 10 power minus 9 or minus 10 at zero bias. at VG0, it should be as low as possible. The current should be as low as possible. Then we can able to achieve very minimum offset current, and that will further give rise you I on-off switching ratio. So that is why this subthreshold slope is again a limiting factor. So how to achieve, if you see the relationship, this is a simple relationship you can find in any textbook. So S is nothing but dou Vg by dou log ID. So how much change, or you can say the tenfold change in current because of voltage change. And there is an exponential term e power minus VGS divided by eta kt, and if you calculate that, you will get ID is 10 for a BZ of 60 millivolt chain. So that relation is there in any textbook. And if you find out here, the relation is 1 plus semiconductor capacitance CS divided by C insulator capacitance, and this term 60 millivolt per decade. Now the beauty here is, if you can make this sign positive to negative, then we may achieve 1 minus. Okay, because our target is we should go beyond 60 or below 60. But if you look into this positive term, so it may comprise 1.3 or 1.4, and if you multiply further 1.4 into 60, it will obviously give you above 60. But how to make this plus sign, or you can say positive sign, to negative? Then you can achieve 1 minus CS by C insulator, and it will give rise you 0.8 or 0.6, anything. It may be anything below 1. And if you multiply 60, that will give rise you less than 60 millivolt per decade. That is for sure. So now we need to search certain materials who can give rise you negative capacitance, so that we can make 1 minus, right? So here is the key. That is why people are exploring so many ferroelectric materials. So which are the ferroelectric materials can provide you or can give rise you negative capacitances? Okay, so I'll show you 2-3 structures. One is MFIS, or you can say metal ferroelectric insulator and semiconductor, and another one is MFMIS. So MFMIS is metal ferro metal insulator semiconductors. So these two kind of structures or architectures are going on, how to achieve this 1 minus term, and that will give rise you below 60. Okay, so summary, all this summary, if you merge together, then we can have a lot of leakage currents. You can find out, one is due to drain induced barrier lowering, another one is due to punch through, one is gate direct leakage, and another one is here body leakage because of this junction PN junction. So there are a lot of leakages coming to picture if you summarize all the short channel effects, and that is why one beautiful quote is here by Professor who is saying small is beautiful, because we are going to scale, we are going to functionality diversification, we are going to reduce the cost. Many things we can achieve due to scaling, or that is why called small is beautiful. And another contradictory statement is off is not totally off. Because of all these short channel effects, you can say in off condition, when VGS is 0, still there is some current flow, which is because of the leakage currents or short channel effects. So that is why it is called off is not totally off. So these two codes are always in trade-off. One is small is beautiful, another one is off is not totally off. And finally, how to get rid of these challenges. So there are a lot of mechanisms, lot of methodology, and I think in this FTP almost many things are going to be covered. So here I'll cover, one is improved device architecture. So this part, and another part is 2D materials. Okay, how to incorporate 2D materials to enhance the mobility and enhance the drain current. And again, there are a lot of architectures, different contacts, how to make good ohmic or Schottky contact. So all these things are also there. And similarly, many people are trying for high K dielectrics, how to reduce the gate leakage, and other materials like trinitrate or indium gallium arsenide, silicon germanium also. So there are a lot of research going on. So I'll only cover this one and a little bit about NCFET. So first, let's start with this SY. So if you look into this silicon on insulator, and there are two architecture. One is partially depleted, another one is fully depleted. So partially depleted means the body thickness is little bit high as compared to the fully depleted. That means the body is not fully depleted by the depletion region. So if you look into the mechanism, there are accumulation region, there are depletion region, there are inversion region. Again, in inversion, there are weak inversion, strong inversion. So all these things are there. And if you just the terms or the name suggests partially depleted, the body is not fully occupied by the depletion region. And similarly, the fully depleted means the body is fully occupied by the depletion region. So there are two different configurations in SOI. So here, dependent on body thickness, how much body thickness you are taking TSI. And if you see the journey started with single gate SOI and double gate here in 2 gates, multiple gates, and similarly tri-gate or FinFET technology. So either people are going for new materials. As I told, there are silicon germanium, strain, graphene, 2D materials, many things. So either one hand is material to search new materials. Another hand is how to invent novel architectures or new transistor structures. So these are the two ways people are doing research, how to go further scaling or further performance enhancement. And if you look into the SOI structure is buried oxide is sandwiched between the body and substrate. So this is the insulator, and this insulator will restrict your depletion region. So this depletion region between N plus and P, between source and body, and here also drain and body, these both are restricted because of this insulator, and it cannot go beyond beneath the insulator. And what it will give rise? It will restrict the body leakage. It will restrict this body leakage also. So there are a lot of advantages, and gate control also it will enhance a lot of advantages in this PDSY or FDSY. Even if you see all the RF switches nowadays are manufactured with PDSY only. And why FinFET? Why FinFET means when people started proposing this FinFET. So one is at that time, this is old news. At that time, people started 32 nanometer, and there is a proposal before 32 nanometer or up to 32 nanometer, bulk CMOS can take care, or bulk CMOS can be taken care up to 32 nanometer, and below 10 nanometer non-silicon devices. But still silicon is going on now also in 5 nanometer technology. But when FinFET is in proposal, so there is a talk, why FinFET? And this gap between 32 and 10 can be fulfilled by FinFETs or multiple gate FETs. So FinFET means there are 3 kind of control from 3 sides. Okay, top side and two lateral sides here. Okay, so there's a better channel control and a better on-off ratio, improved subthreshold slope or SS. So everything can be achieved due to this FinFET architecture. And what should be next? So if you look into these 2 diagrams, I have just taken it from IEEE EDS newsletter. Electron Device Society newsletter, July 2020. So July 2020, there is a article. One is FinFET. This same figure, if you see, so there is a this is your fin, and fin is covered by 3 sides of gate. One is this side, top side, and this bottom side, this side. And now next one is gate all around. If you look into this gate all around, the complete silicon channel or whatever the channel is completely circulated by gate, or wrapped around, you can say wrapped around from all sides by gate. So the next is like people are talking after FinFET mass production, there may be gate all around come to picture. So the ideal MOS transistor is gate all around, fully surrounding metal electrodes, fully enclosed. So everything is good advantages in case of this, but still people are going on this FinFET technology also. And this is a old data from Amazon and Flipkart. If you look into this Amazon site and Flipkart site, I've just taken the screenshots, nothing else. So Amazon here, they started selling OnePlus, and similarly Flipkart also selling all these Xiaomi products or Samsung products. Now, if you go to the product description, so the description says 1+3. Now, again, if OnePlus started selling, I think, a Nord 5G, or you can say OnePlus 9R 5G also sold in Amazon. Now, this is the 1+3 old news, and they started using 14 nanometer FinFET technology. Similarly, Samsung also started using 14 nanometer FinFET process in their Exynos 7 Octa, and the famous Xiaomi, Redmi, they also started 14 nanometer FinFET in long back, way back. So with all this motivation, we started exploring FinFET in our laboratory or here. So we started with Fin devices by taking care of ITRS roadmap, so International Technology Roadmap for Semiconductors. And in this roadmap, we found there are 3 applications. One is either you can go for high performance, or you can go for low operating power, LOP, or again, final one is LSTP, low standby power. And with these 3 different applications, we started designing the device, whether what should be the fin height, what should be the fin width, and gate length, everything. So HFin and LG first we tried to optimize the device. What should be the fin height and fin width, and fin height we just varied from 5 nanometer to 26 nanometer. Similarly, fin width also varied from 5 nanometer to 16 nanometer. Just it is a division with LG. If you multiply 0.25 into 20, it will give rise you 5 nanometers, right? So similarly, all the variations of HP were simulated, and results are extracted for all these cases, 0.25 to 1.3, and starting with transconductance, on current, off current, threshold voltage, everything is evaluated. And here on current is exported with I think with the VGS at VDD, and off state is calculated with constant current method. Here, if you look, sorry, threshold voltage is calculated with constant current method. So what is constant current method means? Drain current 100 nanoamps, what should be the gate voltage? So that is nothing but constant current method. And I think when you start with S device and S process, they may give you how to calculate all the parameter extractions in CentOS TCAD. Okay, now if you compare the performances or transconductance or threshold voltage or on-off ratio, anything. So here we found like SFin for 22 nanometer case is giving you higher ID and higher transconductances, and similarly 26 nanometer also giving you a better in case of on current and transconductance. But the thing is, threshold voltage is going to reduce. So always there is if you are one hand getting high on current and another hand you must get high leakage also. So there is always a trade-off between on and off currents. Okay, similarly, other parameters like capacitances, cutoff frequency, everything is evaluated in AC simulation. So all these things reported here, and you can just compare for which HFin height, what is the cutoff frequency, and what is the cutoff frequency here for 1.3 case. So all these things are reported here, and further the similar kind of analysis are done for WFin. And if you look into this WFin height, just our aim is how to achieve a optimum fin height and optimum fin width. And this kind of fin width variation also has been done here with 0.25 to 1. And this shows the output conductance, there is a little bit reduction, or you can say lower GD. Lower GD is a desirable case, because if you look into the gain, so GM is GM upon GD is nothing but gain. And for narrow WFin, we can achieve low GD, so which is again one beneficial case. And similarly, the capacitances and cutoff frequency also evaluated, and we found like if you are keep on increasing fin width, so there will be a poor gate control. Okay, and if you are keep on increasing fin height, there is better performance, but the problem is leakage current is high. So we need to find out what is the optimum fin height and what is the optimum fin width. So in this case, finally we categorize the device with respect to aspect ratio. Okay, so with respect to aspect ratio means what is fin height and fin width. There is a ratio between width and fin height. And if you look into this x-axis, so one is going beyond 1, okay, 1.2, 1.5 to 2.1. Another one is below 1, that is 0.9, 0.6. So that means if you are going below 1, which is nothing but the denominator is high. So denominator is h fin. So fin height is high means your ratio will be less than 1. And similarly, fin width is high means your ratio will be greater than 1. So one case we are taking planar device, which is W fin is high. Another case is FinFET, which is fin height, H fin is high. Okay, so they didn't only you can focus with numerator and denominator. So one case numerator is high means planar and denominator high means this FinFET. Okay, and both are equal means it's nothing but a tri-gate, or all three sides are taking care of channel and it's ideal tri-gate. So we categorize the device with respect to this ratio, or you can say fin height and width ratio. And if you look into this device, or you can say the dimensions, one is cutoff frequency parameters. We calculated cutoff frequency, offset current, delay, and power dissipation. And in certain cases, if you design in this way, you may achieve high cutoff frequencies. Okay, if you can see here for 0.6 case, it is giving you high cutoff frequency. And similarly, if you can design in this way, planar device with 2.1 or something, so you may get. Okay, so all these cases. And similarly, intrinsic delay, if you need more or less delay. Okay, suppose you need less delay, then you may design with respect to a tri-gate design, so that you can achieve a low delay. So as per your requirement, what is the requirement, whether you need high frequency or whether you need less delay, or whether you need low power dissipation. If you need low power dissipation, you can go with this planar architecture. Okay, so depending on the requirement, or you can say whether you need a high performance or low power or low standby power, whatever your requirement, you can design the device. Either you can go with a high aspect ratio or low aspect ratio, or everything. So this work we just reported here in IEEE Transactions on Nanotechnology in 2015. And further, there is one more thing, that is how to integrate multiple technologies into a single thing. So multiple technology means one is ultra thin body. So ultra thin body means your body is too low, so that your gate control will enhance. So one is UTB and FinFET. So how to integrate FinFET and UTB together? So if you compare these two diagrams, so one is UTB line is here and fin is above this. Okay, fin is built above the UTB line, and whereas if you compare with conventional FinFET, there is no UTB. There is no UTB. Only fins are grown above the bead oxide or above the box. So in this architecture, this is also called inverted T-FET. So this is just if you rotate it, invert it, it can look like a T shape. So this line and this fin. Okay, so this is nothing but inverted T-FET, and we started exploring this architecture and published many articles in IET, in Springer and elsewhere. I'm not going the details about the FinFET because a lot of things I need to cover. So finally, if you look into the fabrication aspect, so fabrication aspect means there are a lot of complicated fabrication processes. So one is if you look into the lithography process, ion implantation process, diffusion process, there are a lot of things, oxidation, metallization. So maybe fabrication guy can comment on this, but I know there are a lot of complicated fabrication processes, and due to this complicated fabrication process steps, we may not get a ideal fin shape. Okay, we may not get a rectangular perfectly 90-degree ideal fin shape. So that is why we started exploring, okay, what should be the case if the theta is something different from 90, and you may get a trapezoidal shape instead of a rectangular, you may get a trapezoidal case. So what should be the case if theta is not non-90? Then we started exploring in both the hybrid case, what is together UTB and FinFET. So this together UTB layer is there, 5 nanometer, and FinFET is also there with fin angle variation. So angle is like taken 80, 85, 87, 90, something like that. And we started varying. So what should be the impact of angle, or you can say trapezoidal case. So trapezoidal case, theta fin, if it is non-90, then you can look into the current graph. So ID and VG. So ID VG is giving you something low here. This one is 80 degree. Okay. And similarly 85 and 87 and 90. So if your angle is not perfectly 90, then you may get a low current. So ID is significantly increasing for higher theta pin. That is why I mentioned here in red color, as well as larger H pin. So larger H pin case we have seen earlier, and theta pin also we are looking into now. And all these parameters like threshold voltage, subthreshold slope, on current, everything is extracted from the simulation results. And here is for 90 case, you can see subthreshold slope is nearly equal to 60 or 63.59. Whereas if you are getting a trapezoidal case, so it is deteriorating, going 66, 65, everything. And similarly, we found out capacitances and what is the delay, CV by CV upon I, and CV upon I also it is too good in case of 90 degree. You can see the delay is continued shrinking or reducing for 90 degree case, and it is like exponentially increasing for in case of trapezoidal case. So all these things calculated and evaluated. And finally, the total power and what is the leakage power. So leakage power also here you can calculate C, but there is a degradation in leakage power in case of 90. So in case of 90, you may get little bit high leakage. Rather, we can compromise with this because we are getting a lot of advantages. We are getting high on current, we are getting low SS, we are getting delay, low delay, many things we are achieving for 90 degree, but with a little compromise in leakage power. So all these things we reported in IEEE transactions on electron device and material science and semiconductor processing in 2017. And one more thing, this is the last one in case of FinFET. So in case of FinFET, one more thing is if you think about your space application, right? If you go into the ISRO or whatever ISRO is doing, so one device also we saw from Semiconductor Laboratory Chandigarh. So they are looking into radiation hardened devices. So how the radiations can be tolerated by the devices. Okay, suppose you can imagine in case of a space, there are a lot of high energy particles. There are alpha particle, beta particle, gamma particle, again cosmic rays. There are a lot of high energetic particles, and if these energetic particles will collide with your integrated circuit, or you can say anything, whatever satellites or radars or whatever things are sent to space. So if it will be collided with integrated circuits, then suppose you can imagine one example. So you need logic 1, or you can say logic 0. Suppose our requirement is logic 0. But because of this bombardment of high energy particles, it may generate some EH pairs, electron hole pairs. And due to this EH pair generation, some charge carriers may be collected at drain side. Okay. And because of this charge collection, you may experience a current. And that current may give rise to logic 1. Instead of logic 0, it will give you logic 1. Right? So, which will malfunction the complete IC because our requirement is logic 0, but due to this ion strike or ion bombardment, we are getting a logic 1. So that will completely destroy the function. So that is why people are searching how to build a device which can tolerate, or how to build a IC which can tolerate high radiation strikes or high radiation energies. So that is why we just taken a simple exercise for among 3 devices. One is normal MOSFET. Another one is hybrid device, which is a integration between UTB and FinFET. And the third one is UTV fin and some spacer technology. You can look into the spacers. One is we have taken Si3 and 4, another one is hafnium oxide. So these three architectures are taken, and ion has been striked at the same position for all three devices with same energy. So that is what the aim, and we have strike the same position and same energy to compare which device can tolerate the energy particles or high energy bombardment. And you can just focus into this. If the ion strikes here, they can make a funnel kind of shape. So this funnel may have certain radius. Okay, so this radius also will vary, and look into how the radius variation of radiation may hamper the device. And one more is track length. So this is track length and track radius. Two parameters are there. And when the ion strikes, that is the time. Okay, so striking time and almost three parameters. One is striking time, another one is track radius, and one is track length. And now we can compare all three devices because we strike the same position, and the energy is 10 MeV per mg per centimeter square with a linear energy transfer LET. And if you compare all three devices, so this is the prompt component and this is the delayed component. What is the transient current we are getting, ID versus time? So this ID is quite high in case of conventional FinFET. And remember, here I'm not applying any biasing because we are only focusing on the ion strike. So because of this ion strike, we are experiencing some current due to the charge collection, and this current is here for all three devices. So one is conventional, one is hybrid case, and the third one is spacer with hybrid. Now if you compare all three devices, the prompt component is quite high in case of conventional, and this tail component also almost same for all devices, but you can look into the prompt component here. The prompt component is minimal for the third device, which is spacer and hybrid device, and it can tolerate certain amount of energy. This signifies it can tolerate certain amount of energy as compared to the other two devices. And here I just taken here before ion strike how this contour plots are looking like. Okay, so contour plots may be your S process or S device. The people who are taking, they will give you. So contour plots here after ion strike 10 picosecond and after ion strike of 100 picoseconds. And if you can compare this, the energy density, this is little bit high in case of the hybrid devices. Here almost 1.9 into e power 20, and whereas it is only 1. So a little bit high as in case of hybrid devices, and that will further facilitate our transport mechanism from source to drain. Okay, and what is the heavy ion generation? Okay, how much heavy ion is generating because of the ion strike? And as I told, similar position I striked for all three devices at the middle of channel. So at the middle of channel for all three cases, and if you see this UTV layer is certainly helping us. Why? Because all the generation, whatever ion is generating, almost it is, if you look into the red color, so UTV layer is contributing or taking care of this ion generation. Whereas in case of this normal device, everything is accumulated in the channel or towards the drain side. Okay, and that will give rise to high current or charge collection, high charge collection. Again, like I told, so three parameters. One is track radius, another one is track length, and further characteristic time when we are striking the ion. So I just compared between just take one diagram, any one diagram. Suppose here I have taken two radiuses. One is 20 nanometer and 70 nanometer, right? So two track radius in each case, you can see for all three devices. So we can compare between the track radius, what is the difference or drain current, or you can compare among the devices. Okay, so among the device means this is conventional, this is hybrid, and this is spacer with hybrid. So when you are comparing, and that is why for a easy comparison, I made all y-axis similar. So all y-axis you can see it is 0 to 7, 0 to 7. Okay, so that we can make a easy comparison. Okay, which current is large, and because all axes are similar. So now I can just look into this 20 nanometer and 70 nanometer case. So if your track radius is too high, then we may accumulate all the EH pairs in that track radius, not in the drain side. So charge collection may be less in drain side, whereas it will be collected in the EH as a EH pair inside the radius or inside the track, ion track radius. Okay, that is why we can experience a less current. And if you compare among the devices, so among the devices, you can look into this black line or this red dotted line. So this hybrid FinFET, they are giving very low current as compared to the conventional one. Okay. Similarly, here if you come to spacer with hybrid, it is again very less. Okay. So that it suggests like your hybrid device with spacer technology can tolerate little bit large amount of ion as compared to the conventional one. So this is what we concluded from all these three devices. And finally, the bipolar amplification and charge collection. So how much charge collected for which device? So this three device, we just made a comparison. Again, here also, the third one is giving you very low charge collection as compared to other two. Okay. And what is bipolar amplification? So bipolar amplification is nothing but how much charge is collected and how much charge is deposited. This is just a ratio between collection and deposition. And deposition almost is same for all three devices. Only the difference is charge collection. So if you compare here, the charge collection is too high for conventional one. So that is why the bipolar amplification is too large. Whereas the bipolar amplification is too low in case of the third device, which is spacer with OB, or you can say hybrid device, UTB plus FinFET. So that is why we can say the third device is little bit resilient, or it can resist to the ion strike, okay, as compared to the other two. So this data just we reported in IEEE transactions on device material reliability, TDMR, in 2018. Okay, so this is about our FinFET work. Now coming to this 2D materials. Okay, so what is 2D two-dimensional materials? As I told, we may have graphene, we may have molybdenum disulfide, tungsten disulfide, WS2, or MOSE2. So everything they have only 2 dimensions. They don't have a third dimension. Okay, so that 2 dimension is giving us ballistic transport. And one more thing, remember the all equations, the modeling part, everything will different as compared to silicon, because they don't have even third dimension. You don't get per centimeter cube. If you talk about doping in silicon, then that is a per centimeter cube, or you can say centimeter minus 3. But here, whereas in case of 2-dimensional materials, it may come centimeter minus 2 or centimeter square, right? So while doing the modeling part, you must take care of all the data, all the units, everything. So let's see. So why graphene is popular? And because this one of my PhD scholars work this one. So graphene, if you look into the EK diagram, or you can say energy momentum diagram. So these are also called zero band gap semiconductor. Why there is no band gap? Because at a certain point, you can look into this EK diagram. At certain points, they are merging together. The conduction band and valence band, they are merging together and giving you these are popularly called as billowing zone, and this is called zero band gap semiconductor. There is no gap between conduction band and valence band. So that is why the you can see the linear dispersion. The linear dispersion is perfectly coinciding and merging at Fermi level, and there is no difference between EC, EV, or Fermi. Everything is a single line, and band gap is 0. Right. So this is the problem of graphene. Also, you can say, what is the problem? Because of this 0 band gap, we cannot make the graphene FET totally off. Because why? There is always a flow between conduction to valence band to conduction band. Okay, there is always an exchange, energy exchange, because they are merging at certain points. So it is very difficult to make the device off or to make the transistor off. So how to make the transistor off also, it's a challenge in case of graphene FET. Now graphene has lot of opportunities, lot of things, because it can be applicable to flexible material, and the bendability is too good. It can be useful for a you can say for a wearable device. You can stitch it in your t-shirt or pants or anywhere to generate some amount of energy. So here one is flexible graphene FET encapsulated in hexagonal boron nitride. One manuscript I have taken from ACS Nano. So to show the lot of opportunities in case of graphene FET. And now the challenge to us is how to make the graphene FET a suitable one, or you can say to create certain amount of band gap so that we can make the transistor off. Okay, because it's very hard to make it off. So how to generate some band gap? So there are a lot of mechanisms to create band gap. So one mechanism is cutting larger area graphene sheet into graphene nano ribbons. Okay, how to cut it? And if you are cutting the nano ribbons, then we are altering the property. And if you are altering the property, you may generate or induce some band gap. So similarly, another is just compress it or stretch it. Okay, tensile it. So that is also one mechanism to induce some band gap. And other is the final one is doping the graphene. So which attracted us, and we started working in this. So how to dope substitutionally, not interstitially. You remember one thing. So whenever I'm just you can focus this blue color. So blue color means I'm just taking one carbon atom with a foreign atom. Okay, with a foreign atom is occupying the carbon atom. Instead, the interstitial sites, there is no interstitial doping. Only I'm talking about substitutional doping. Okay. So if you can very carefully substitute one carbon and deposit one foreign atom, it may be nitrogen, it may be boron, then we can maintain the linear dispersion, like I have shown the linear dispersion of EK diagram, and we can induce some band gap. Okay. So this one we started working in this, and from literature we have taken like 6.25% of doping is inducing 0.36 electron volt of band gap, and similarly 12.5 and 18.75, everything is just reported in literature with all the fabrication data. Our task is we need to model this graphene FET with carefully, and to find out what is the quantum capacitance, what is the channel potential, VCH, and quantum capacitance. Because if you see the equation, I just ignored all the mathematical things. If you are interested, you can find my papers in IEEE Explorer. Okay, and just CQ, we need to find out what is quantum capacitance. So quantum capacitance is nothing but the relation is here channel potential. Okay, so these are the two important parameters. One is quantum capacitance, one is channel potential in case of graphene FET. Now we need to model this quantum capacitance carefully, and with some percentage of doping. Now you can look into one case, the first diagram. You can see the dotted black color line. So dotted black color line means there is no gap. Okay, it's perfectly linearly dispersed and conical shape and touching at 0, right? So this is the undoped case. There is no gap. Now, if you look into the 6.25% or 12.5 or 25% of nitrogen dope, then you can see this one. There are certain amount of gap has been generated or created or induced. Okay, and this gap is little bit increasing if you are increasing the percentage of doping. So here 6.25, 12.5, and 25, right? With a left shift because we are doing nitrogen. Similarly, if you do a boron, so it is just similar with the right shift. Okay, and this quantum capacitance modeling was just reported in IEEE EDTM, this Malaysia. And finally, we started with a you can say self-consistent modeling. So without any manual work or without calculating manually everything, we just given an initial guess. So this is just a flow diagram, flow chart, you can say. Just we started modeling this graphene FET backgated source drain, and this is SiO2, and this is a substrate, and the equivalent diagram is here VCH, and this is quantum capacitance or top capacitance, whatever the notation says. And our main target is channel potential. We should give a initial guess, okay, and it will automatically calculate what is seed charge and what is quantum capacitance, okay. So these two, and it will check whether our condition is satisfied or not. If it is satisfied, then it will give you solution. If it is not satisfied, then again it will take another guess, and it will flow the same process. Okay. So this is self-consistent modeling without any manual work. The code has been written in such a way that you can just give a channel potential guess, and it will give you result if the condition satisfies. So with this, we just model the graphene FET, and this just IDVG. We match with measured data. So on measured data to validate our model. So to validate the model, we match with experiment, and it's quite matching perfectly. You can look into this lines and dotted lines. Okay. So and further the mobility also. Again, mobility is mobility we have to model properly, carefully, because it's not a silicon case. It's completely different material, which is a graphene with certain amount of boron doping. And further we calculate what is the seed charge density in both cases for 12.5% doping in case of boron doped, in case of nitrogen dope. So all these things we calculated. And two things here you need to focus. So one is how much saturation it is giving, whether the saturation is good or not, because if you are going to apply as an amplification or as an analog device, your saturation should be very good, so that it can reproduce the same signal with certain enhancement, okay, certain amplitude modification. So your saturation, how good it is. And the second one is whether it is giving you low leakage or not, or we can make it off or not. Two things we need to take care. Just you can compare with the dotted line and solid line. So if you look into this dotted line, so first I am focusing on offset leakage. So if you see this dotted line for undoped, this violet color on doped case, dotted line, and which is giving you very high leakage, right? Very high leakage. And now if you can increase the doping concentration, and you can see this red color or any blue or green, anyone. So solid line, this red color is giving you very low leakage in terms of 10 power minus 6 or minus 7, right? So that we can make the device off, little bit off as compared to undoped case. So this is one condition. Second condition, the saturation, good saturation behavior. So good saturation, you can see this dotted line. The dotted line is going linearly, which is not at all applicable for analog or RF application in any case. And this is undoped. And if you can see this percentage of doping 6.25 is giving you very good saturation, and all these cases also very good saturation. So that it can be applied for analog or amplification process. Okay, so this one we just published recently, is available in early access IEEE TED. And again, similarly, by taking this equivalent diagram and all this modelings has been written in Verilog A, because we want Verilog A is nothing but an analog model, Verilog analog. So this one we tried to check the linearity behavior. So what is the linearity behavior means? We need to check what is the higher order transconductances, higher order GM1, GM2, GM3, again the distortions, whether the distortion is high or low for RF application. So RF application, we evaluated all these parameters, and by writing a Verilog A code in cadence vector, making it symbol, we just tested a single tone and multi-tone perspective. Single tone means single frequency, multi-tone means multi-frequency. Okay, so all these applications we checked whether HD2 is high or low. Similarly, what is intermodulations, what is current intercept points. So if you compare the device, this one is Spectre, this one is model, and this one is reference. We just match with our work with some reference work, and this one is doped one. Okay, so undoped one is minus 55.66, whereas doped one is giving you 57.33 and is a negative scale, right? So negative means it is slow. Even if it is 57, it is 55, but it's negative. So we can able to reduce some amount of distortion in case of doped case, okay, as compared to undoped one. And this work was just reported in ITCDS recently. And finally, what are the devices in race? So what are the devices in race? If you, there are a lot of devices, but I'm just focusing these three devices. So one is FDSY, and mostly European industry. One is STMicroelectronics, one is CELAT. Okay, there's a French company. So CELAT and ST, they both are focusing on FDSY. So and there is a report that 28 nanometer FDSY may be good for quantum computing. And again, it may be good as per their statement. It may be very good for low temperature applications, or you can say cryogenic temperature applications. And similarly, again, one more is negative capacitance FET, NC-FET. Like I told, how to make this one plus to minus, one minus. And this insulator we can achieve by taking some ferroelectric material, negative capacitance. Okay, so that we can achieve a below 60 subthreshold slope, and that will further give you leakage current low. Okay, and one more device is nanosheet transistor. So nanosheet transistor means this is just a, I think it will come as a mass production in next 2022 or something. So nanosheet transistor, so we can just put a sheet of you can say instead of FinFETs, you can just rotate it and make it sheet. Okay, so multiple sheets you can insert inside the gate, and the gate will control from all four sides, right? So this side, and two sides, and the channel will be fully controlled by the gate, and it will further improve your gate control and allow low bit descaling, so everything. And if you look into the opportunities are quite high. There are a lot of special calls from APL, Applied Physics Letters. You can say the deadline was over. Even if the deadline was over, I'm just saying for your what are the opportunities in the devices. So here on September 15, 2020, one call was there, ferroelectricity in hafnium oxide materials and devices from APL. So we also are doing little bit to another PhD scholar is working in NC-FET. So what is this NC-FET? We just taken one HSO. Okay, so silicon doped hafnium, or you can say just hafnia silicon. That is silicon doped HFO2. Okay, so silicon doped HFO2, that is HSO. So we have taken metal, ferro, metal, insulator, and semiconductor. MFMIS. So this one is the one structure we are looking. And one more thing, in case of NC-FET, there is one famous that is nothing but LK equation, or which is called Landau-Kalatknikov. Okay, LK equation can be found out. V ferro is a relation between thickness of ferro and what is the polarization charges Q. And this alpha beta, anyhow I neglected gamma also here. Plus one more term is there, but gamma is negligible, so I neglected gamma. So alpha beta is dependent on material property. What are material here you are taking, whether it is HSO or some HZO or anything. Okay, depending on the ferroelectric material, alpha beta will be different. And what is the polarization charge and what is the thickness of ferroelectricity, and then you can able to find out what is the ferroelectric voltage. So this is just a hybrid modeling. You need to find out the charge from TCAD. So first model this device in TCAD, find out what is the polarization charge. So after getting the polarization charge, you need to solve the LK equation. So after solving LK equation, you can find out what is the ferroelectricity in that, or you can say ferro voltage here. So once you will get ferro voltage, then it will be added to gate wires. Okay, what is VGS plus V ferro? So that means there is an amplification in gate bias. So again, you need to match this S curve and what is polarization and electric field curve, and just we matched it perfectly, this S curve. And then further we calculated because we need to avoid the hysteresis. Okay, right? So you can observe this hysteresis. it's just a zoom version. So for if you are keep on increasing this HSO thickness, or you can say ferroelectric thickness, so once ferroelectric thickness reaches a limit, it will give you some hysteresis, and we need to avoid this hysteresis for a good good circuit or device application. And again, we varied with the back bias, this back bias, and how back bias can be a beneficial to NCFET. And with achieving this or with modulating this back bias, we can able to reduce subthreshold slope below 60, and we can achieve 55 millivolt per decade. This is just we reported in IEEE EDL, not published, it is in review. And this one again, TSMC 2 nanometer chip, I already explained this one. And this National University of Taiwan, NTU and MIT, they are searching, this is only in R&D, not in mass production or anything. So just TSMC has given one task to NTU and MIT to research in 1 nanometer chips. Okay. Now switching the topic. So switching the topic, I'll take hardly 15 to 20 minutes more. So this is about BioFET. Okay, so I'll talk a little bit about biosensors, and then some open areas. Okay, open areas, neuromorphic power devices, and all these things. So first start with BioFET. So BioFET here, if you look into this, what is the concept here? So main target is it should be level free. Okay, there should not be any color change or anything. It should be level free. By measuring the electrical characteristics, we can say whether the biomolecules are present or not. So how to measure the biomolecules? How to measure the biomolecules? Here one concept is you can just create some cavity. Okay, some cavity has been created here in between the gate contact and oxide. Okay, and in that cavity we can put some biomolecules, and because of the biomolecules, the capacitance here it will change. Because the occupancy of biomolecules, the capacitance will change, and further it will change the charge, and then the drain current. Okay, so simple mathematics, it is nothing physical concept. So if you are putting some biomolecules, the biomolecules are having certain amount of permittivity and certain amount of charge, and that will further alter the capacitance. And if it is altering the capacitance, your drain current will change. So this is a simple concept. Then we started taking of DNA biomolecule. So DNA biomolecule, from literature we got the permittivity is 8, and it is a negatively charged. The charge is negative and the permittivity is 8 almost. So then we compared between two devices. One is NPN, another one is PIN. Okay, so this is a simple comparison between N-channel IM-FET and N-channel tunnel FET. And by varying the occupancy of DNA biomolecules, then DNA biomolecules may be horizontally aligned, or you can say maybe vertically aligned. Okay, so if it is vertically aligned, then the gap here will be reduced. Okay, and the gap here will be reduced means the capacitance will further change. And if it is horizontally aligned, that means the gap will increase. Again, it will alter the capacitance. So depending on the alignment, whether it is vertical or horizontal, or you can say angle of biomolecules, the gap will change and capacitance will change. That is why we've taken 3 parameters. One is charge, another one is permittivity, another one is angle of biomolecules. So 3 parameters, and we checked what is the change in current, what is the change in threshold voltage, and what is the sensitivity. So sensitivity will be calculated like without biomolecule, what is the current, with biomolecule, what is the current. So that will give rise to sensitivity. So given between 2 devices, one is tunnel FET, another one is ion FET. And these 2 devices, if you compare, the sensitivity is quite high in case of tunnel. Similarly, here also I just plotted the transconductance gate voltage for both the devices with variation of charge. And angle also, if angle is 0, that means it is horizontally aligned. If angle is 30, it is little bit towards vertical. And the sensitivity has been compared between the devices. And finally, we just made a comparison table. So here one IMFET, one TMFET, TFET, tunnel FET, and 3 parameters. One is negative, one charge, one is constant K, dielectric constant, another one is angle. So if you look into all the cases, so here the variation, threshold voltage, how much, and all this sensitivity, and you just compare the sensitivity here 2.255, here it is 3. So in all cases, I think tunnel FET is outperforming and it is giving you very good sensitivity as compared to the IMFET. And this was just reported in IEEE Sensor Journal last year, one of my dual degree student work. And finally, another one is this is one accumulation or inversion mode. The previous one we just compared between inversion mode and tunnel FET, and this one is accumulation, or you can say junctionless. So junctionless means N plus and N plus. So there is no junction between this N plus and channel and this N plus and channel. And similar fashion, we calculated the energy Venn diagram for both the device. So which device is giving you more sensitivity, or which can be applicable for biosensors or biofed. And similarly, this work is being reported here in AU Elsevier. And this contour plots also calculated for different K, K1, K5, K8, and K12 permittivities. And here you can see the electron profile. The profile is like AMFET is and IMFET, both the cases, accumulation mode. And you can just look into, first it started with yellow, then slowly the densities are increasing, or electron profiles are increasing. Whereas here it's quite constant. There is no change if you are changing K. If you are changing the permittivity, there is very minute change. And similarly, line graphs also you can see the current has been changed far away, or you can say the charges for 0 and the charges for 1 point minus 1.0. The current has been, there is significant shift in the current as compared to IM. Similarly, what is the sensitivity? Sensitivity for all cases, AMFET, IMFET, and all 3 devices. So what is accumulation mode, inversion mode, and N channel and P channel. So all these cases we will just compare and find out. I'm not going in detail. So we found like accumulation FET, or you can say junctionless FET, is outperforming and it is giving you good sensitivity, can be applicable for a very good sensor. And finally, I found one paper from SES Nano. This one is SES Nano. So they have demonstrated one graphene FET, okay, graphene FET based biosensor, which can be useful for rapid detection of COVID-19. COVID-19 virus can be rapidly detected by this graphene field effect transistor biosensors, and we are just searching some literature and interested to work here and not started. And the final part of my presentation. So final part is neuromorphic computing. So if you look into the how to mimic our brain, okay. So how to mimic our brain means we have a lot of synapses and lot of neurons. So we have many neurons. Suppose we are looking into emails, we can look into many aspects. Okay, so all these aspects can be taken as input. So all these aspects can be taken as input, and it will sum, and then it will further processed. So that is why this is one presynaptic neuron, and this is postsynaptic neuron, and these are synapses. So our aim is how to mimic our brain with energy efficiency. Okay, we can energy efficiently how to mimic our brain and with an accuracy. So one is energy efficient, area, and third part is accuracy. So these 3 parameters need to be taken care while talking about spiking neural network or any kind of synapse based devices or neuron based devices. Okay, so whether you are designing a good neuron which can give you very good accuracy and which can be energy efficient and which can be designed with a less area. So all these 3 things need to be taken care while designing any synapse or any kind of neuron. And whenever there is this action potential will be there. If this action potential will reach your threshold, then some spikes will be generated. Otherwise, there should not be any spikes. So that is spiking neural network, or you can say SNN. And further, it will give you output. And I just taken some literature. This one is from Nature Scientific Reports and from EDL. And they just reported there are a lot of leaky integrated fire neurons, LIF-based neuron, either for a CMOS or SY based. So here one is SY based neuron in 32 nanometer technology. And what is the, just you can see the benchmark table. The benchmark table says the area, one parameter is area. And the second one is what is energy per spike. So your energy per spike should be very low. That means it should be energy efficient, and the area should also low with the low technology, and the accuracy. Accuracy is another important parameter. So accuracy means, suppose after making a spiking neural network, it's supposed to identify some, or it's supposed to solve a classification or some image recognition, any kind of problem. With certain amount of accuracy. So this one is another EDL one, which is I think from IIT Bombay. So they have just reported on bulk FinFET. So bulk FinFET with area of 0.04, and energy per spike is also too low, that is 6.3 into 10 power minus 15 joules, which is till time I think it is optimum, but it is not. It is theoretical. Again, it's not a practical one. It's a theoretical one. And similarly, one from Kaushik Roy's group from Purdue University. So Purdue University, they have just reported one LIF neuron based on magnetoelectric switching of ferromagnetics. So similarly, they have designed one synapse, and some people are going for synapse, some people are going for neuron. So either you can go and design a very good neuron, or you can go and fabricate or design a synapse. And this one is one of the ideal one. So EDL one, they just design one synapse, and after making a synapse, they integrated into a network. And after making a network, they applied for a classification accuracy. So what is just taken one classification problem, whether it's red color or it's a blue color or any kind of classification, image recognition or image classification, anything you can take. So the accuracy is not that good. It is still under research, like 84% they are proposing, which is not at all good. And one more recent report, this is in early access of IEEE TED. So machine learning added device simulation of work function fluctuation for multi-channel gate-all-around silicon nanosheet MOSFET. This is also one very good article I found, and I just for your sake of knowledge, I placed it here. So this is all about your neuromorphic. The final one is power devices. So what is power devices? Just if you compare these materials, silicon, gallium nitride, and silicon carbide, and one more interesting material is beta gallium oxide. So beta gallium oxide, you can just compare the band gaps. So band gap here is 1.1 electron volt, everyone knows, at room temperature, right? And if you look into this gallium oxide, the band gap itself is 4.7 to 4.9, which is too high, and it can tolerate, and you can just see the breakdown electric field. The breakdown electric field is 8, which is too very much high. So it can tolerate high electric field, it can tolerate your high voltage, high power, everything. So it will be very good application in case of power electronics, or you can say the power devices. So there are a lot of opportunities, lot of calls. You can see this ultra bandgap semiconductors. There is special call from APL. Even the deadline was over, 2020. Again, one from TED. One special call was there. New simulation methodologies for next generation TCAD tools. Just recently, this February, the call was over, and here 28 February. But if you are interested, one more upcoming call is there, which is from transaction on nanotechnology, IEEE T Nano, special section on neuromorphic computing, which is coming 30 September. If you are interested, you can submit articles here on neuromorphic computing, 30 September 2021. So this is all about my presentation, and if you are if you are interested in device area, you can propose new devices, new concepts. Either you can go for modeling. Again, modeling, there are a lot of methodology. One is lookup table method, one is physical method, one is empirical, or one is compact model. And if you are having TCAD tools, you can go for simulation. And if you have facility, fabrication, characterization, again, another area. And finally, whatever device you are proposing, you have to implement in circuit design. So all these are research in device area. And in my group, we are publishing some notable work like in APL, Applied Physics Letters. So this one became a featured article by the editors. And IEEE, TDMR, JEDS, TNANO, all this just focusing and targeting. And coming to my collaborations and support. So collaboration I am just doing with Professor Raskin from UCL, UVN, and Dr. Somya from SRM, and Laurent from French Aerospace. So all this is my collaboration. Dr. Samar from past president from IEEE division. And if you are talking about funding, so without funding there is a very limited scope to research. So I want to thank my institute and to DST sir for funding the work. So with this note, I'm concluding my presentation. Any valuable questions or suggestions are welcome.
Thank you, sir, for your valuable time. Any questions from the participant side? So there is a question in the chat box.
Okay, 1 second.
Is there any other method except constant current method for threshold voltage?
There are a lot of methods. Threshold voltage extraction can be done from GM curve also. If you find Yanis Davidis' book, Professor Yanis Davidis, there are 3-4 methods how to extract threshold voltage, either from IDVG or from GMVG. 3 different methodologies are there to extract threshold voltage. You can just find in Professor Yanis Davidis' book, MOS modeling. Any other question?
Any other queries, participants?
Good evening, sir.
Yes,
Sir, while we are showing IDVGS curve, sometimes we will show current in ampere per micrometer. So, what is the specific reason, sir?
Nothing else, because by default this simulation tool, no, it is taking in micrometers, right? If you your session will be there in center of TCAD in S device as well as S process. So whenever they are designing any lithium or any doping, so everything comes as a micrometer by default, this simulation tool. So whenever we are getting some results, some people are reporting as per micrometer, and some people are converting into actually only in amperes. So it depends. That is not a big deal. You can find out.
Okay.
It's basically this any TCAD tool, whether it is Atlas, Silvaco, or Centeros TCAD, or any tool, they are by default micrometers.
Okay, sir. Thank you.
Yeah, thank you. So there is another question from a participant. Yes. What is ferroelectric materials?
Ferroelectric materials. You can find there are different materials, right? Depending on the polarization of charges, para electricity, ferroelectricity, you can find out, right? It was there in intermediate, right? You can search in Google. That's simple.
Are there any reference books for FinFET amplifiers?
Any course to design FinFET data amplifier. Okay. I'll take. 2 lambda coefficients vary with thickness of. No. With thickness it won't vary. Alpha, beta, gamma it will be same for a particular material. Okay. With thickness it won't vary. Maybe it will vary with temperature, but not with thickness. And a reference book for FinFET amplifiers. FinFET, there are many books. If you find from Professor who one book is there, again Professor Chauhan, Y.S. Chauhan from Kanpur, IIT Kanpur, you can find one very good book, modeling of FinFETs. Okay, FinFET based devices. Again, they have also reported how, and if you are familiar with BSIM, Berkeley short channel IGFET models, so there are BSIM CMG, BSIM SY, BSIM 3v3, and BSIM bulk. So all these different models are there, and BSIM bulk is nothing but BSIM FinFET only. You can find BSIM website or Professor Chauhan's book FinFET modeling or Professor Chenming Hu's group. Okay, Berkeley. Those books you can find, a reference book for FinFET. That is purely for FinFET modeling. Again, what is there? To achieve low power dissipation, we go for positive threshold, which includes high K, which leads to higher delay, low FT and low and max Fmax. To achieve higher FT and Fmax, reduce delay, which technique we will need to use. Okay, so your target is to get a high cutoff frequency and high maximum operating frequency, right, with a reduced delay. So that, like I told, you can achieve with either you can go with material or you can go with device architecture. And if you look into this gate all around device or nano seed transistor also, I saw some literatures reporting very good high Fmax and FT with low delay. You can try with nano seed transistors if possible, or gate all around device. Okay. Can you share session 2 feedback? Okay.
Any other queries from the participants?
Sir, I am having one doubt, sir.
Yes, please.
You have touched about the neuromorphic computing, sir.
Yes.
In the neuromorphic computing, how the device will be looking, how the structure or
same, sir. Same device, whatever we are showing now, like whether it is a SY or let's go here. Wait 1 second. Here. Suppose this one you can see the read the title. So leaky, integrate and fire neuron by charge discharge dynamics in floating body MOSFET. It's a simple partially depleted SY MOSFET. You can download this paper. This simple partially depleted SY MOSFET, which can be applicable for neuromorphic application. Same device, but the application is different. Similarly, if you see here, this same bulk FinFET, okay, same FinFET, but it designed such a way that it can be applicable for neural networks or striping neural networks. Okay.
So the memory also will be in the same device itself, or
there is one, not memory is not required. Only I can say one thing: impact ionization. One mechanism is there, impact ionization, which can lead you for neural network application. So how it will lead you? If you download this paper, there are energy band diagrams.
Okay.
TSY can give you impact ionization because the body thickness is too high, and there are some floating body. And because of this floating body, there are some ion generation, and this ion generation can give you a negative feedback. Negative feedback in the sense a drain to channel to source, because our carriers are flowing from source to drain, source, channel, and drain. But because of this impact ionization, it will give you a negative feedback from drain, channel to source. So that is nothing but your whatever you are talking memory, kind of. Okay, because of this negative feedback. And everything, I think, impact ionization. So that is why this one also bulk FinFET, they designed in such a way that the body thickness is too high, so that it will support impact ionization.
Okay, sir.
And here also you can see device type, all SOI, RAM, bulk FinFET. So similar devices. Some people are going for memory star, some people are going for FinFET, some are going for random access memory. So it's a simple comparison. And device is same, but the design is such that it will be applicable for neuromorphic computing.
Okay, so what if you have shown one special issue? I have also gone through it previously.
Yes.
So if we want to compete for that, what kind of result we have to produce, or what will be the challenge?
Like I told you, you can target 3 parameters. So one parameter is your energy per spike. Suppose you are going for spiking neural network. The energy per spike should be as low as possible. With a low area, the device dimension or the area should be low.
Okay,
And
okay.
third one is accuracy, but you may find difficulty to apply as a network and to solve a recognition or classification problem. You forget about accuracy for the time being. You can focus on energy per spike and area.
Okay, okay, okay. Okay, sir.
Anything else?
Any other questions are there from participants side?
Hello, sir.
Yes, yes, please.
What is remnant polarization and what should be its value for better performance? High or low?
When you are talking about negative capacitance, right?
Yes,
So
sir.
we are focusing on this remnant. That is nothing but charge. Actually, if you see this FinFET, let me take to that slide. 1 second. Here. So here, this is nothing but P is same. If you find out E versus polarization, either field versus polarization, electric field and polarization, or you can also convert into ferro voltage and Q. This is just like nothing but V volt per meter, and if you multiply meter here, it will come as Q charge. So our target is we need to find out Q from the TCAD, right? And this value, it depends. It sometimes higher charge may be beneficial for a voltage amplification. Sometimes lower, if it is beyond certain amount, it may give rise you this hysteresis. So for this hysteresis also you need to take care. You cannot say like higher charge may be beneficial, or you keep on getting high charge, it will be beneficial. It is not like that. Sometimes hysteresis may come to picture. So we have to avoid the hysteresis, as well as we have to amplify this voltage. For that, we need to optimize the remnant polarization, or you can say the charge, right?
What should be its value, sir? Should be minimum or maximum?
No, like that.
For choosing a material, see, different material has different coercive field. And
You can take maximum value, okay, to get a good amplification of voltage, right? If your Q is high, then you can get a good voltage amplification, because it's just a alpha multiplication and a plus term is there. So two important factors you need to keep in mind. One is ferro thickness, and as well as this Q. You can take high for a good amplification, provided the hysteresis should not come.
okay.
Okay.
Okay, sir. Thank you, sir.
Sir, one more question is there from the participant side. What is the future of carbon nanotubes in the nanoelectronic devices?
Yes. I think today Professor Karmalkar covered nano wire transistor, right? Yes. So carbon nanotube future is there, but see, from practical implementation till now, silicon is there. No one has been replaced silicon. For 5 nanometer also silicon is there. For proposed 3 nanometer also silicon will be there. I don't know. It depends on foundry, how they are adopting the technology and how they are adopting the things. But it may take time, but still future is there, carbon nanotube. It may take time, okay, to develop the infrastructure, to develop the technology. But to replace silicon, it is very hard. Okay. Let's see how the foundries can go. But everything is in research. You can carry on, no problem. Our work is just R&D. We can propose something, we can report some data, It depends on foundry what they will accept or adopt.
Any other questions are there from the participant side?
Sir, nowadays IBM and TSMC, they are focusing on 1 nanometer, 3 nanometer devices now, sir.
Yes, yes.
So actually we can, in our simulators also, we can do 1 nanometer LG or 2 nanometer or 3 nanometer LG devices, and we can publish papers, sir. We get good results.
No, but you should take care of the physics, right? Not
Yes, sir.
the basic physical models won't support, right? If you go below 3 or 2, so you have to include all the advanced models. The maybe the drip diffusion model won't support. Maybe the basic mobility model won't support. Like we are taking CVT model, and those models may not support in this below technologies. So you need to find out advanced models and incorporate it. Or the easiest thing is go for modeling. Okay, mathematical analytical modeling. Then you can do some simulations. But if you do simple simulation, people will ask questions. It is a huge question mark. In a such technology, how you are getting results in normal simulation?
Because some research papers we are seeing 1 nanometer and 3 nanometer gate length papers also, sir, in very good reputed journals. So if we mimic the, if we improve that architectures with the reference, we can go.
But you calibrate your tool, right? With a
Yes.
good fabrication paper, you calibrate your tool. Then you may adapt those models and methods. But important is those models and methods. Okay, what are the models you are using?
Okay, sir. Okay, sir. Thank you, sir.
Because all quantum phenomena, everything will come in such a low technology node. The
Yes,
normal
sir.
models may not work, or it may work because it's a simple tool. You can give you that input, it will give you result, but those results are questionable. Okay.
Okay, sir.
So there's another question in the chat box.
Yes, yes.
Can you share what graphical tool is used for your publications?
We are working many tools, like one is MATLAB modeling. Whatever graphene fit I have shown, that is purely mathematics, and it was done in MATLAB modeling. And another work I have shown in IET CDS, that is also graphene, that is in Cadence. Cadence, we have written Verilog code in Spectre, and then done all the analysis in whatever single-tone and multi-tone analysis. So that is related to graphene, and whatever FinFET work I have shown, that is in CentOS only, CentOS TCAD. And whatever NCFET I have shown, so NCFET work is a hybrid kind of model. Some part is like to find out the charge, we are using Silvaco. Then we are going for MATLAB to solve the LK equations. So many different students are working in different areas and different tools. Depends on your availability.
I think I doubt whether the particular participant is asking regarding the how graph is created, or
Oh, okay.
I'm not clear about it. If he is if he is clearing it,
can you speak it out, Arul? Or what is the doubt? Is it about the graphs?
like Origin Pro or something?
Origin, yes. We have done in Origin only. Origin and these are MATLAB. These are from MATLAB graphene fits, whatever I have shown.
So there's another query just above. He is meaning graph tools.
Graph tools. So it is Origin Pro only.
Origin and these graphene fits are MATLAB.
There's
one more question. What is
before that? Arul, sir, is any possibility to analyze charge molecules in FET for biosensors?
Yes. That's purely simulation only. Whatever we have done. charged biomolecules. Only you need to take care of permittivity and charge the things. Okay, you have to do a extensive literature to find out what are the biomolecules, because for a particular biomolecules the acceptor, or you can say the receptor. Okay, there are two things: one is target molecules, one is receptor molecules. Okay, so the certain biomolecules has to react with the receptor. The target has to react with the receptor, then only your charge or your electrical properties will change and characteristics will shift. So to find out, you have to do a literature of what are the particular biomolecules you are looking into. Then you can write code as per the syntaxes and how to vary the permittivity, how to vary the charges, all these things. It can be done in simulation only. Yes, origin trial versions are available, I think, for 1 month.
Sir, you have shown some that the cadence, something you have shown, no, sir?
Yes, yes.
Is it connecting the TCAD to cadence, or anything you are incorporating from?
No. That can be done by lookup table method, LUT method. But here, this one is not connecting cadence to TCAD. This is purely written in Verilog A in cadence
Verilog.
vector. Verilog A.
Okay. So it's a circuit based.
But it can be done. It can be done in LUT. One of my BTech student has done for his device.
Okay, so this work is based on circuit only, purely.
This work is by writing Verilog A, making it a symbol, then performing the single tone and multi-tone analysis in Spectre. Here I have written Spectre, right? This model means analytical model, and this one is Spectre.
Sir, incorporation of data into lookup tables means we need to have CGS, CGD, and we need to put it in lookup table.
All data like ID, BZ, every data you have, then you can incorporate in LUT method.
Okay, sir. Or then we can have circuit extractions from cadence,
yes,
no, sir?
Yes, correct.
Okay, sir. Thank you, sir.
Thank you.
Another one question is there, sir. Which tool can be used for biosensor simulation?
Any TCAD you can take.
TCAD.
No issues. Any TCAD, either Silvaco or Centeros, anything. There are a lot of papers, right, in BioFET. Okay. Anything else?
Any other questions are there?
Any other, then please ask. Otherwise,
So there's a question in the chat box.
yeah.
Can you suggest something for mixed mode Silvaco?
Mixed mode simulation you can do, right? In any Silvaco or Centeros, mixed mode simulation you can do to find out all the H parameters or Y parameters, and then further FT, Fmax, everything can be done. Just check the manual, you can find out mixed mode simulation. How to find out Y parameters, H parameters, or for cutoff frequency, FT, Fmax, because you need Y parameters, right, for FT, Fmax. Your device, yes. I think when your Centeros session will go on, no, S device and S process they will give you. So first you need to design your own device, then you can solve it. So in solve section you can define mixed mode simulation. Okay, device may be same. You can go for DC analysis, you can go for mixed mode analysis, you can go SC, everything.
Sir, have you used process simulation
Some of my students have done process also.
How will you publish that, or how you will take that to an article?
Same. Actually, process means we are just doing half, then half will be mirror imaged.
Okay.
That way it is done.
So in that way you will be explaining the process steps.
Yes. No,
you'll be suggesting something, or
not in detail. Only writing like how much time for diffusion or how much time for oxidation. That thing we have to write.
Okay. So that may help the fabrication people.
Yes. Charged biomolecules result in biodevice using TCAP. You can create a cavity, and in that cavity region you can put some charged molecule. There is syntax. You can write what is the interface charge, or what is the biomolecule charge for a particular region. You can define everything, right? I think they are more interested to learn the tool, right? So your centerless session will help. Centerless process, centerless device will help. Okay.
Yes.
Okay then. If any further queries, you can drop a mail. Yes, it's simple.
It is really a very interesting session, sir.
I don't know. This post lunch session will be very hard. Always very challenging.
Actually, this is the first session. This much question we are getting.
Oh, okay. Really?
Almost like 20 minutes for question answer. 20-25 minutes.
Again, I was wondering, like, after Professor Karmalkar and Dr. Nirmal, what I will speak.
It's very interesting, sir.
Okay.
We are able to see most of your results and your analysis, your publications.
Yes.
It's a really useful session for us, sir.
Thank you very much.
For those people who are doing research, they will research in this field. It will be a much useful session, I guess.
Yes. I hope they will get interest and start working. Anyhow, so solar cell I didn't include here because again it will take 1 hour.
So probably we will have another time we will.
Yeah, no issues. We'll have some future engagement, no problem. Okay.
Yes, sir. Okay, sir. Thank you so much, sir.
Thank you.
Participants, actually, please wait for another 5 to 10 minutes. Tomorrow's session will be, as you all know, tomorrow's session will be 2 sessions will be for MATLAB. So kindly use that session properly. So I hope many participants will be having MATLAB with you.